Dual-clutch automatic transmissions utilize two main wet clutch designs. 1. Concentric clutch, also known as a nested-type clutch. This design features both plates aligned in the same vertical plane, resulting in a more compact assembly. 2. Parallel clutch. This design arranges the clutches side by side. Gear arrangements. The 1, 3 and 5 synchronizer assemblies are powered by clutch 1, while clutch 2 drives the 2, 4 and 6 reverse synchronizers. The vehicle starts moving when the 1, 3 synchronizer engages first gear with clutch 1 activated. The transition to second gear occurs when the hydraulic servo shifts the 2, 4 synchronizer, followed by the release of clutch 1 and engagement of clutch 2 for the 1, 2 upshift. Subsequent shifts follow the same process, utilizing pre-shifting or early shifting of the synchronizers, with the actual gear changes happening as the clutches cycle. Drivers can operate the transmission transaxle via a floor-mounted shift lever or paddle shifters located on the steering wheel. Both clutches are activated by hydraulic pressure, similar to that found in conventional automatic transmission clutches. Disadvantages: compared to traditional automatic or continuously variable transmissions, CVTs, dual-clutch automatic transmissions transaxles have certain drawbacks. 1. They lack the torque multiplication benefits provided by a torque converter. 2. They generally do not achieve the same level of fuel efficiency as CVTs. A dual-clutch transaxle essentially comprises two distinct transmissions housed within a single casing. Each section is driven by its own clutch, with power transferred sequentially as these clutches engage. This design mimics an automatic transmission while employing a manual transmission-style layout and synchronizers along with two countershafts. The shifts occur rapidly, relying on the speed of each clutch's engagement and the ability to partially engage one clutch while the other slips during transitions. Key speed sensors include engine RPM sensor. This sensor, positioned on the clutch drum housing, relays the engine RPM to the transmission control module, TCM. Odd gear input, shaft speed sensor, provides the TCM with input shaft RPM data for odd gears, 1, 3, 5 and reverse after the C1 clutch. Even gear input shaft speed sensor supplies input shaft RPM information for even gears, 2, 4 and 6 after the C2 clutch. Temperature sensors monitor clutch fluid temperature, measures the temperature of fluid exiting the clutches. Transmission fluid temperature, gauges the temperature of fluid within the transmission. Oil temperature sensor, located on the TCM, this sensor tracks the transmission oil temperature. The TCM leverages these temperature readings to adjust system pressure, control the clutch, manage cold start conditions, and protect against overheating. Pressure sensors. Pressure sensors relay information regarding the hydraulic pressure within the clutches to the TCM, which provides a 5-volt supply to the sensors. These sensors measure oil pressure, allowing the TCM to adjust solenoids for precise clutch pressure control for each clutch. Position sensors. Position sensors include fork position sensors. These sensors inform the TCM about the positions of the 4 gear shift forks managing transmission shifting. This includes positions for 1R, 3.5, 2.4 and 6N. Transmission range sensor, TRS. This sensor indicates the actual gear selection, P, R, N, D. The TCM utilizes data from these sensors to determine the necessary clutch and shift servo operations, activating or deactivating actuators to manage hydraulic pressure, gear selection, clutch control, and shift locking. A typical dual-clutch automatic transmission transaxle incorporates the following solenoids. Line pressure. Solenoid, LPS, manages system pressure by directing hydraulic oil for clutch activation, shifting and cooling, then returns oil to the sump. Clutch cooling flow, solenoid, CCFS, regulates hydraulic oil for clutch cooling. Shift cooling, multiplex solenoid, SHCMS, controls the gear shift fork positions and clutch cooling. Clutch shift multiplex solenoids, CSMS1 and CSMS2, manage pressure for odd and even clutches during shifting and control clutch cooling flow. Clutch shift. Pressure solenoids, CSPS1 and CSPS2, regulate hydraulic pressure for odd and even clutches. Clutch pressure cut, CPCUT, a safety valve that manages pressure release within the hydraulic system. Shift select solenoids, SHSS1 and SHSS2. Manage shifting for respective gearshift forks. Shift fork position. The TCM operates the shift solenoids, which apply force to the shift forks via lever points, enhancing the force applied. Each sentence can be long if the input requires it, but must not exceed 30 words. If a sentence is longer, split it into 2 or more natural sentences without altering the content.
Positioned between the engine and the transmission transaxle, the torque converter serves several key functions. It transmits and amplifies engine torque. It functions as a clutch between the engine and the transmission transaxle. It permits slippage, enabling the transmission to remain engaged even when the vehicle is stationary. The torque converter consists of 3 main components. Impeller. This component, also referred to as the pump, rotates with the engine and is found on the transmission side of the converter. Turbine. Located on the engine side, the turbine is driven by fluid directed by the impeller's vanes, causing it to rotate and engage the transmission input shaft. Stator. Acting as a reaction component mounted on a one-way clutch, the stator redirects fluid flow to enhance torque multiplication. Each of the components features curved vanes, optimizing fluid flow direction and increasing hydraulic efficiency. The impeller and turbine are designed with split rings to facilitate fluid movement. The torque converter operates similarly to 2 fans facing each other. The impeller is the powered fan while the turbine acts as the non-powered fan, both being driven by transmission fluid. The fluid connection between the impeller and turbine allows for the absorption of sudden changes in speed or torque. The stator's vanes are curved in the opposite direction of the impeller and turbine, allowing it to redirect fluid flow and multiply torque. Torque converters are typically single-piece welded assemblies and are not designed for disassembly or straightforward repair. In the event of failure, they are usually replaced as a complete unit. Torque converter flex plate. A torque converter is generally mounted to a flex plate, a thin metal disc that connects to the engine's rear flange. The flex plate often has a pilot indentation for the converter's nose and replaces the traditional flywheel used in manual transmissions. The flex plate's function is to smooth engine vibrations, which the torque converter's weight effectively handles. An external ring gear is typically attached to the flex plate's rim or the torque converter cover, engaging the starter motor to start the engine. In some hybrid vehicles, a torque dampener plate may replace the torque converter, serving a similar function without the internal fluid elements. Torque converter drives the pump. The oil pump drive shafts usually run through the converter, connecting internally to the housing via splines. The torque converter also drives the transmission oil pump, often referred to as the front pump. The drive hub connects the oil pump to the converter, ensuring the pump only operates when the engine is running. Transmission input shaft. In most rear-wheel drive setups, the converter drives the input shaft directly, with splines on the turbine connecting to the shaft while the stator hub mounts to a one-way clutch. Torque converter operation. Fluid sent from the transmission oil pump enters the torque converter, where it is picked up by the impeller's rotating vanes and transferred to the turbine, creating both rotary and vortex flow. Torque multiplication phase. Torque multiplication occurs as fluid exits the turbine, strikes the concave side of the stator, redirects, and pushes against the impeller. This phase enhances the torque transferred from the impeller to the turbine, particularly at lower speeds when the impeller operates significantly faster than the turbine. Coupling phase. When the speed ratio reaches 90% or higher, the converter transitions into the coupling phase, with rotary flow dominating over vortex flow. In this phase, the turbine and impeller rotate nearly synchronously, reducing torque multiplication as the stator's role in fluid redirection diminishes. Stall speed. Stall speed refers to the maximum engine speed at which the impeller moves without rotating the turbine, resulting in the highest torque multiplication ratio. Normal operation. When shifting from park or neutral into drive, some engine torque is transmitted to the transmission input shaft, causing the vehicle to move slightly, known as creep, which is typical for automatic transmissions. torque converter diameter. The diameter of the torque converter and the angle of its stator blades influence stall speed, with smaller converters achieving higher stall speeds and greater torque multiplication at elevated engine speeds compared to larger converters. Lock-up torque converter.
Lock-up torque converters enhance fuel efficiency by minimizing slippage using a torque converter clutch, TCC, creating a direct mechanical connection between the engine and transmission.
Converter clutch control.